Far past the orbit of Neptune lies a vast and frozen ring of ancient debris called the Kuiper belt. We assume that this region was just a junkyard of inert, frozen rocks tumbling silently in the absolute dark. But what if we were wrong? Meet an object currently designated as 612-533-2002-XV93. It is a tiny ball of water, ice, rock and organic-rich materials, measuring only about 310 miles wide. To put that into perspective, you could drive across the entire world of XV93 in about 5 hours. It hovers nearly 4 billion miles away from the Sun. By every law of planetary science we thought we understood, XV93 should be a completely silent, frozen, dead block of ice. But according to a groundbreaking new paper published in the journal Nature Astronomy, it isn't dead at all. XV93 has an atmosphere. Welcome to Territory. This is your space. If you want an atmosphere, you need two things. You need a source of gas, and you need gravity. Gravity traps gas molecules and prevents them from floating away into the vacuum of space. And to get gravity, you need mass. Earth has plenty of mass. Our gravity easily holds onto a thick, heavy blanket of nitrogen and oxygen. If we look out into the Kuiper belt, there is exactly one object we previously knew possessed an atmosphere: Pluto. But Pluto is a massive dwarf planet. It is nearly 1,500 miles across and has enough gravitational weight to hold onto a thin, hazy atmosphere of nitrogen, methane and carbon monoxide. XV93 is a pebble compared to Pluto. It has a fraction of the mass and a microscopic fraction of the gravity. Any gas on the surface of XV93 should immediately boil off into the void, completely unbound by the rock's weak gravitational pull. Furthermore, because it is 4 billion miles away from the warmth of the Sun, any gas that did somehow stick around should instantly freeze solid and fall to the ground as frost. It should not be a gas at all, yet observations prove that it is. Its atmosphere is incredibly thin, about 100 times thinner than the atmosphere of Pluto and roughly 5 million to 10 million times thinner than the air we breathe. But the sheer fact that a rock this small and this cold possesses a gaseous halo completely shatters our understanding of the outer solar system. So, how did we detect an invisible layer of gas around a rock we cannot even see? A team of researchers in Japan found it using a technique called a stellar occultation. Using a network of ground-based telescopes spread across Kyoto, Nagano and Fukushima, they aimed their lenses at a specific distant background star. They had calculated the exact moment that XV93 would drift perfectly in front of that star from the vantage point of Earth. As the tiny icy rock passed by, the telescopes recorded the data, and the instruments registered a soft, gradual dimming before the star vanished. That dimming was the starlight scattering through a hazy, invisible layer of gas, a mathematical proof of an atmosphere. Based on the way the light bent, the researchers believe this alien sky is likely dominated by methane, nitrogen, or carbon monoxide. But discovering the atmosphere is only half the battle. How is a rock this small generating gas in the deep freeze of space? Theory number one is a violent cosmic hit and run. The Kuiper belt is vast, but it is also chaotic. Millions of frozen objects share this orbital highway. Sometime in the relatively recent past, another smaller object may have slammed directly into XV93. The extreme friction and kinetic energy of that impact would have generated a sudden, massive burst of heat. That heat would have instantly vaporized millions of tons of surface ice, creating a temporary, gaseous halo. If this theory is correct, the atmosphere we are seeing today is just the lingering smoke from a cosmic car crash. It is temporary. Because XV93 does not have the gravity to hold onto it forever, this impact-generated atmosphere is slowly bleeding out into space. Some of it is escaping, and some of it is freezing and falling back to the surface like a microscopic, invisible snowstorm. But theory number 2 is much stranger: cryovolcanism, ice volcanoes. What if the atmosphere isn't a temporary accident, but the result of being constantly replenished from the inside? We usually think of geological activity as a trait reserved for large planets. Earth has a hot, molten core that drives volcanoes and earthquakes. We assume small rocks in the outer solar system are frozen solid all the way through, but XV93 might be hiding a warm secret. Deep beneath its frozen, cratered crust, there might be ongoing internal activity. This could be driven by the slow decay of radioactive elements trapped inside its rocky core. Or, if XV93 has an undiscovered moon, the gravitational tug-of-war between the two bodies could be generating internal friction. This internal heat would warm the volatile ices trapped beneath the surface. As the pressure builds within the core, the icy outer shell of the world would physically crack. Through these massive fissures, freezing, vaporized gases would vent and seep out from the interior and into space. If cryovolcanism is actively happening on XV93, it changes everything. And if a rock this small can be geologically active, it implies that there could be thousands of other, small, dynamic worlds hiding in the outer dark, venting their own hidden oceans and gases into the void. We have discovered over 6,000 planets outside our solar system: massive gas giants, planets made of boiling lava, puffy planets with the density of cotton candy, and frozen ice worlds. Occasionally, we find a rocky planet sitting right in the habitable zone. But the term habitable zone is a bit of a trick. It just means a planet is at the right distance from its star for liquid water to exist on the surface. But without an atmosphere to trap heat and provide pressure, liquid water cannot exist. Now, what if I told you that we have found the strongest evidence yet that a rocky planet in the habitable zone has managed to hold onto an atmosphere? The planet in question is named LHS 1140b, orbiting a red dwarf star about 48 light-years away in the constellation of Cetus. Red dwarfs are the most common type of star in our Milky Way galaxy. They are much smaller and much cooler than our Sun. The host star here is only about 18% the mass of our Sun. Because the star puts out so little heat, its habitable zone is pulled extremely close. LHS 1140b orbits its star at a fraction of the distance between the Earth and the Sun, completing a full year in just under 25 days. When astronomers first spotted this planet, they used 2 primary methods to figure out what it was. The radial velocity method measures how much the planet's gravity tugs on its star. This gives us the planet's mass. The transit photometry method measures how much light the planet blocks when it passes in front of the star. This gives us the planet's physical size. When you have the mass and the size, you can calculate the density. Initially, the calculations suggested this was a completely dry, incredibly dense rock with a massive iron core. It sounded like a terrible place to live, but later measurements paint a different picture. The planet is roughly 1.7 times the radius of Earth, but its density is much lower than scientists originally thought. The math points to a water world. Some estimates suggest somewhere between 9 and 19% of this entire planet's mass could be water. To put that into perspective, if you took all the oceans on Earth, they would account for just a tiny fraction of 1% of our planet's mass. But there is a catch, though. Knowing a planet has water is entirely useless if the planet is too cold. Based purely on the amount of light and heat it receives from its small star, this planet has a baseline temperature of roughly minus 47 degrees Celsius. At that temperature, all of that potential water would be locked up in a global shell of solid ice. The only physical way to melt that ice is if the planet has a greenhouse effect, and to have a greenhouse effect, you need an atmosphere. Finding an atmosphere on a small, rocky planet is incredibly difficult. The glaring light of the host star usually overwhelms the faint chemical signatures of the gases surrounding the planet. To get around this, researchers used a high-resolution spectrograph and looked for one specific element: helium. Helium is a very light gas. On a rocky planet with an atmosphere, helium tends to rise to the very top layers. As starlight hits this upper layer, the gas slowly escapes into space, creating a large, extended cloud around the planet. When the planet passes in front of its star, the starlight has to filter through this escaping helium cloud. The gas absorbs one very specific wavelength of infrared light. By capturing the spectrum of the starlight that reaches our telescopes, scientists can look for that missing wavelength and prove the gas is there. And they found it. They detected a clear signal of helium escaping from the outer atmosphere of LHS 1140b. It is the first time anyone has ever detected an atmosphere on a rocky planet inside the habitable zone of another star. However, the detection of helium does not mean the planet is inhabited. Helium does not support biology, but its presence proves that this rocky planet has successfully held on to a substantial gas envelope for billions of years. We know that keeping an atmosphere is remarkably hard, especially if you orbit a red dwarf, as they are notoriously violent stars. When they're young, they frequently unleash massive solar flares and intense bursts of ultraviolet and X-ray radiation, enough to completely strip away a nearby planet's atmosphere. The LHS 1140 system is at least 3.1 billion years old, meaning it has had billions of years of radiation to potentially strip the atmosphere away. And yet, remarkably, the atmosphere appears to have survived anyway, holding on far longer than researchers expected. We actually have proof of just how easily that atmosphere could have been lost right next door. There is a second, smaller planet in this exact same system, called LHS 1140c. It orbits much closer to the star. When the team analysed the light passing by this inner planet at the exact wavelength helium absorbs, they found no trace of that helium signal at all. It was too close to the blowtorch. LHS 1140b, sitting farther out, appears to have survived where its neighbour did not. Because we now know this planet has an atmosphere, the possibilities for what it looks like on the surface open up considerably. If the lower layers of that atmosphere contain heavier greenhouse gases like carbon dioxide, the surface temperature could rise significantly above the freezing point. This raises another possibility. Like many planets orbiting very close to small stars, LHS 1140b could be tidally locked, meaning the gravitational pull of the star would force the planet to show the exact same face to the star at all times, one side in permanent daylight, the other in permanent freezing night. If that turns out to be the case, and if the planet does hold a thick atmosphere and abundant water, it could resemble what astronomers call an eyeball planet, a dark side locked under a permanent shell of ice, and a day side warmed by the star and insulated by its atmosphere, potentially hosting a liquid ocean under constant sunlight. A planet that would look, from space, like a giant eye staring back at its star. The next step is more detailed observation with the James Webb Space Telescope, whose infrared sensitivity can detect gases in the deeper layers of that atmosphere, revealing whether it contains carbon dioxide, carbon monoxide, or water vapor. We know the air is there. We just need to find out what's in it. What do you guys think? Let me know by dropping in your comments below. And as always, don't forget to subscribe to Territory, because this is your space.